Good morning, everybody. It is Tuesday, April 14th, 2020, and today we are going to cover um, exponential functions. We're going to build on from yesterday's video. Now, I am sorry that video was so quiet. Hopefully, it is a little bit better today. Just continue to let me know if there's issues like that, if there's something I need to do different. The volume's messed up, something's messed up, please just let me know. I'm on the computer all the time, obviously, so just message me. That's it. Okay, let's um, let's get started here. Don't mind all my tabs open up here. Okay, so today we're going to focus on graphing exponential functions. Just like earlier in the year, we worked with tables with linear functions, and we also worked with graphs. Right? We knew that if we can make a table of values, that easily made it so we could graph a function. It's the same thing with an exponential function. The only thing is now we're working with an exponent. But we've done a ton of that this year. Shouldn't be an issue. So just make sure you're paying attention. You can all do this. This is an important topic. It can, as we get further along, there's going to be some things that are tougher than others. But what we're doing right now, everybody should be able to follow along if you've been doing the work that you should be doing. So, anyways, let's do this example here. I don't have too many examples today. I'm more so we're just talking about why exponential functions work the way they do. Now, this first example, this is kind of, we did one like this yesterday. Same function. There's a little bit more to this table, though. And let's see if you can remember how to do it. Go ahead and pause the video. Try and fill out this entire table. And check in with me in a couple minutes. Welcome back. Hopefully you were able to get the whole table filled out. Maybe the first row is a little tricky, but I did give you this example here, so the rest of it you should have been all set for. So let's take a look at the answers. You should be checking that you got the same thing. Right, we show all your work here. We're plugging in this x. We plugged it in for -2 and the x here. 2 to the -2, that gave us this 1/4. Same thing down here, you plug in -1 for the x. Right, the only thing different with exponentials like this versus linear functions is that this x is now in the exponent. We're not multiplying by the slope, it's just different. So go ahead, you fill out this table just like we usually do. And then I added a little bit more to this table today. We can combine our x and our y's to make a coordinate, or an ordered pair. So we take this x, when x is -2, y is 1/4. That's our first pair, first ordered pair here. When x is -1, y is 1/2. When x is 0, y is 1. And we see that over here. Just the same as we normally do with coordinates. Okay, so let's get on to the graph though. We have a bunch of coordinates. When you have coordinates, you can make a graph. You go ahead, plot these points, and you'll get this as a result right over here. So Notice that these numbers are getting bigger and bigger, faster and faster. We saw that yesterday. Well, you can see that in the graph too. From -2 to -1, it doesn't really go up that much. From -1 to 0, it goes up a little bit more. In fact, it goes up twice as much more. And then from 0 to 1, it goes up again twice as much as it did from here to here. It keeps doubling, going up twice as much as it did the x before. So we know with our linear graphs that we worked with earlier in the year, this wasn't the case. We would get something like this. It was always going up the same amount each time. That never changed. So our slope was always the same thing in this case. And it turns out with an exponential function like this, the slope is constantly changing. And we're not going to worry too much about slope for a graph like this. That's going to be a little bit later on for you in high school. But it is something to keep in mind. So as x becomes more positive, this graph rapidly grows. I'm going to get rid of this blue ink here. Oops. Okay. So as x becomes more positive, the graph rapidly grows. We've already talked about that. Now as x becomes more negative, as it goes this way, the graph rapidly shrinks. Okay? So it's not necessarily, I don't like how I worded that, to be honest. I wouldn't say it's rapidly shrinking, because it's actually shrinking faster from here to here. But it is shrinking towards 0. Alright, if you keep going, this is just going to get closer and closer and closer to 0. It's continuing to cut in half each time. Right? Doubles each time when it goes to the right. Well, it's going to do the opposite when it goes to the left. It's going to halve over and over again as x is getting more and more negative. So let's talk about exponential growth. I believe I talked a little bit about this yesterday, but I want to make sure I'm very clear about exactly what exponential growth is. Because we talked about exponential functions, but exponential growth is a way an exponential function behaves. Right? It's how it's growing. It's how it's increasing. So exponential growth means that it's getting faster, increasing faster and faster and faster and faster as time goes on. Or if you think about it maybe with a population, right? You have just a couple people at first. As the population grows and grows and grows, there's more and more people that are having more and more kids, and the population continues to grow faster and faster based off, how many people there are, right? It's increasing faster and faster over time. Now, exponential growth, it does all behave in that way, but there are, some exponential growth is faster than others. For example, let's look at these different graphs over here. These are all actually parts of exponential functions. Right? This one, if you kept going, you did something like that, maybe it would eventually start looking like what you would imagine. But it's not quite there yet. The growth factor of this exponential function is much less than this one. Now, I do want to talk exactly or about exactly what this graph is because it is interesting. This is some data I found. I think it's kind of outdated now, but it still gets the point across that it's comparing how fast COVID-19 spreads based off basically how how ordinary people are acting. Right? If people are doing the normal thing, going to school, taking the subway, going on buses, all these different things, concerts, without worrying about it, that's what this blue line would be right here. And this refers to the number of infections. So the infections just grow so much faster when you do nothing. Now, you do see exponential growth still when you start doing things like social distancing, um, isolation, different stuff like that, then it's going to slow down how fast this virus is actually spreading. So it is still exponentially growing, but it's not growing. The growth factor is not as high. There's a big difference between this orange graph versus this blue graph. And over time, we're actually finding we're starting to get closer and closer to the point where it's not even exponentially growing anymore. And eventually, it'll start exponentially decaying. But we'll talk more about that later. So, exponential decay, I did just mention that. That is the opposite of exponential growth. Something something exponentially decaying. It starts off rapidly decreasing based off how much there is. If you think about, if you had 100 bacteria and you know that it's decaying at a rate of, it's basically halving each time. Well, if you had 100 bacteria to start, the first time you cut that in half, you're getting rid of a lot of bacteria, right? 50 of it. Now you cut 50 in half again, you're still getting rid of a lot. You're still getting rid of 25, but you're never gonna actually reduce quite as dramatically as you did at the start. And that's how exponential decay works. So it decays really, really fast when there's more of the population. It's based off how much there is of itself, if that makes sense. So exponential decay, something that you will very, very commonly hear it with in science class, at least as you get older, is with radioactive decay. Um, I mentioned yesterday something about carbon dating. It does use decay. Um, Something called half-lives too, um, which are related to exponentials, but something we're not going to talk about yet. So you can see exponential decay is very similar to exponential growth. If you look at the examples here, you see that the only difference is we have a negative exponent here, you have a negative exponent here. You do have a positive one here, but the base is less than 0. Right? That 0.1, that's actually a 1/10. And I could swap that to 10 to the negative 1. And well, if we use our properties of exponents, we have that x outside you take x times the negative 1, and that gives you 10 to the negative x. And now that's the same thing as 0.1 to the x. So, and you can see 10 to the negative x looks a lot more similar to these other two functions. Now, if you didn't get this here, don't worry about it right now too much. It's something we'll revisit, but just something I wanted to point out. All right, so we're getting close to wrapping up here, but this is something that is related to the IXL. I believe you're going to find the IXL very easy, especially if you watch this video. In general, for the IXL, you're just comparing linear functions versus exponential functions. You're trying to see which is which. Now, linear functions, we already know these are straight lines. Exponential functions, those curve. So the IXL should be very, very simple. Any graph that's curving is exponential. Any graph that's straight is linear. I think there's only two options for every question. So a little bit of a break on that today, but it's still something important to know. Now, I want to talk a little bit about the difference between a linear function and an exponential function, though. Why do exponential functions grow so much faster? Because if you look over here, you even see this exponential function, it does start off very, very tiny. This linear function is blowing it out of the water for several months at first. But the way an exponential function works, since that x is in the exponent, if this x keeps getting bigger and bigger, if there's more and more time, a lot of times that x is referred to as time, or used for time. Well, as that goes on and on, an exponential growth will always, 100% of the time, always be linear growth. Right, and that's linear growth is right here, and you can see that. Right, this is going to curve upwards. If you give it enough time and you let it keep going, it's always going to eventually pass this straight line. And that's because this x is in the exponent. Over here, we're multiplying by x, so you just keep adding the same amount each time. Since this is in the exponent, it causes this graph to increase by more and more and more each time. Right, you're doubling this over and over and over again, or whatever you're doing, depending on the growth factor. So this will be the last slide here. Just kind of a quick, little quick touch on COVID-19 again. I did say this would be a little bit of a theme just because it does tie in so well with what we're learning in class. So you probably have heard in the news something about flattening the curve. And the idea of that is that we're trying to basically keep a certain amount of people from getting infected so that our hospitals don't become too full. If you are able to slow down how fast people are getting infected, you're able to spread this out over time. If everybody's doing what they normally do, you know, if we were all going to school, concerts, football games, you know, whatever, then it would look more like this. And that's when it gets really dangerous because our hospitals get too full. And this is why we needed to go on lockdown. We needed to turn this curve into this, because this is what it would be if we did things normally. This is what it's looking like now, because we're doing things much better than we did before. There's room for improvement, but it is improvement. There's no doubt about that. So, how does this tie into exponential growth and decay? I do say it's a story of growth and decay in the title. Well, if you look here at the start, at least for a while, it looks quite a bit like exponential growth. Same as over here. That's because it is. The only difference is this red curve has a much higher growth factor, or just a higher one. I don't even know if it's that much higher. It's exponential growth, so every little bit matters a lot. Now, over here with our flatter curve, you see the growth factor's less. So this is the growth. This is the scary part, the sad part of the story. But we're at least getting closer to getting past that. At least things are looking up right now. That's what the data's saying. So, now we're starting to hopefully get to a point where we're going to get into exponential decay. I don't know if we're quite there yet, but when we get there, that's when you're going to start seeing it on the downside, right? Exponential decay. Might take a long time to really finish that off because, you know, just one person here and there might get it, but you do see it does look like those graphs before. And if you look at this red curve, it's kind of hard to see because the green curve's in front of it, but you do see that that would be exponential decay as well. So you can see this curve, this is a lot more dangerous. There's a lot more cases, a lot faster. We want to keep it, we want to take our protective measures, like it says here, and keep things safe for everybody in the hospitals and everybody who needs to get health care. So hopefully you're starting to see why it is so important to understand things like exponential growth. It is very related to the real world. It's the more you use math in whatever job you do, the more exponentials are going to come up. So this has already gone on pretty long. I'm going to let you guys go. Thank you for listening. Have a great rest of your day.